Hello and welcome to today's Tech Talk on Nextmv ML connectors, a price optimization example with Gurobipy, Gurobi ML, and Gurobipy Pandas. My name is Haley and I'm part of the Nextmv team here today supporting this event. Today's presenter is Ryan O'Neill, CTO at Nextmv, and today's session will cover a quick overview of combining ML and OR, followed by a speed run of Nextmv and Gurobi ML. We're saving time for Q&A at the end, so we encourage you to use the Q&A feature at the bottom of your screen. You can also use the chat off to the side. Just keep an eye on that host and panelists versus everyone toggle to make sure that your question or comment goes to the right audience. And with that, I'm going to disappear into the Zoom backstage and let Ryan take it away. Ryan, it's all yours.
Thanks, Haley. And thank you to everyone that is attending today. Today's talk is, I think, a really exciting combination of technologies because what they're doing is sort of giving us new ways to combine these developing fields of machine learning and optimization. This slide is ML and OR, they go well together. And so to give some examples of ways that we use ML and optimization together. For example, we might use traffic or speed predictions to sequence routes for vehicle routing for last mile delivery. We use things like buyer preferences to know what to stock at fulfillment centers. We use ML models to understand things like price demand elasticity for scheduling or product stocking or transshipment and pricing and things like that. And these are things that we do and have done for quite a while now. But what's interesting and what we're going to show today is sort of a combination of technologies that's letting us do this in a new way, where the ML and the OR models are more deeply embedded with each other. So as we've typically done this in the past, most combination of ML and OR has been done historically through point estimates. And what I mean by that is essentially creating constant values that become technological coefficients for OR models, right? And so if we think about when we've loaded examples, we go to some website that provides documentation for an optimization model API. Typically, it'll have input data, and that input data is usually a point estimate that has been provided by some kind of ML algorithm. And oftentimes in the past, that might be an average or a linear regression. These days, it might be something like a gradient boosted regressor or a neural network. But the point is that it's usually a number or a set of numbers, which are essentially inputs to the optimization model. There are also technologies where we can feed multiple inputs. And so maybe we sample from residuals, or we use a parametric distribution to create a bunch of scenarios and feed those into OR models. And those would help us oftentimes represent something like uncertainty or different trade-offs between decisions an optimizer can make. And then finally, we can see things like the L-shaped methods and Bender's decomposition from the stochastic optimization communities, where we decompose OR models and we take uncertainty and put it sort of in a sub-problem. But these are sort of some of, not all of, the different ways that these kinds of things have been approached in the past. And in all of these, that ML model is separate, right? It is not something that the optimization model has direct access to, and it's not something that directly informs the optimization model's understanding of the world in which it's operating. So if you have an OR background, and I think there's probably two types of folks that are at this talk right now. There's people who are coming from the machine learning world who are starting to use optimization. Maybe they've picked up Gurobi, or they've gone to Pulp or Python MIPS website or one of those, and they're starting to apply optimization, and they're thinking, how can I better tie these things together? Or there's probably people from the OR background who maybe learned like I did from the Wayne Winston or the Hillier-Lieberman book, where you crack it open and there's like a bunch of technological coefficients sort of written there for you. And in both of those cases, right, typically the examples are showing us just numbers, right? Here is the data. Well, where did the data come from? In the real world, that data came from observations, databases, OLAP, that sort of thing. And it's either our job or the job of the data scientists that we're working with to create either direct point estimates or hopefully probabilistic forecasts and models that allow us to build optimization models using reasonable inputs, right? So we're not getting, here is the exact price that we should be setting for this item. What we're getting is historical data about price and demand, and we're now being asked to set that price. And so typically we've done that in the past by just creating numbers and feeding that into the optimization. Over time, there have been sort of newer approaches emerging to this. Some of the things that we mentioned earlier, single point estimates, we've always worked in that space. If you think back to the original blending problems or diet problems from the early days of linear programming, those were just using, I think, nutritional coefficients, for example, and those were just known, right? When Bender's decomposition started to be adopted for representing uncertainty, that sort of opened up new avenues. But again, the role of the machine learning model in that is still sort of external to the optimization. At one point, there was a thing called the multiple scenario approach developed, and that sort of leverages horizontal compute, where you can generate a bunch of scenarios, you can sample from those scenarios, and you can try to optimize across them. But again, in that technology, the ML model is once again still sort of external to the optimization. You're generating scenarios and trying to optimize across them, right? So usually some sort of expected value of the objective function. And so fairly recently, there's been a lot of work from places like Gurobi, also like the Skip team, Pyoma team, have been developing integrations between ML model toolkits like scikit-learn or PyTorch and their optimization solvers. And there's different ways that these integrations work. Today, we're going to look at an example that the Gurobi team has given us. All right, so let's briefly give some background to our example, and then we'll dive right into it. This is an adapted example from Gurobi's website. They have an avocado pricing example, so you can find their introduction to it on their website, but I'll show you how we've adapted it to our systems here in a second. So the basic context here is what we think of as the farm share company. We are a consumer delivery service for farm-based goods, and we've recently expanded to offering avocados. And we have historical price and sales data, and we can essentially use that to inform what we should price our avocados at and how many we should ship to each region. And then what we want to do is, optimize our total profit, which is revenue minus cost of waste and transportation. And the question that we're really faced with here is, beyond just saying like set the price to X or or we believe that demand will be Y, how can we tell the optimizer, if you change the price, there will be differences in demand? There is a relationship between these things. And then how can we ask the optimizer to make these choices for us? And that's where this embedding comes in. As I mentioned, this is the starting point. So you can find Gurobi's code for this on their website. And what we're going to show here is not much different than that. What we've done essentially is add our own sort of integration libraries and infrastructure around it to show how you can swap in different machine learning models from scikit-learn and how you can test different estimators within the optimization. All right, so if we're linking OR and ML in this avocado example, we have essentially a number of different features that we give into the model, which are things like the region, so Northeast, Southwest, that sort of thing, whether or not we're operating a peak season, what the historical price and demands and sales were, and then the output of that is essentially an estimator. When we look at the historical way of approaching this, typically, these things are feature data, and the output of the model, the ML model, is also just data. It's point estimates, right? And so the ML model isn't aware of necessarily things like waste or sales, and it's just producing these sort of single numbers for different regions. And we can produce a bunch of them, but again, they're just numbers. When we start to get into the embedding world, this turns it on its head a little bit because things get a little bit more interesting. In this case, what we're doing in the optimization is we're saying the price and the demand are now variables, and we're adding this estimator, which is represented inside of the optimization model, typically as a series of variables and constraints. And so there is a linear, in the MIP world, there is a linearization of that estimator that represents the knowledge that the machine learning model has gained through its training. And so this sort of highlights that difference and how this embedding changes the dynamic for the optimizer. All right, now we're going to dive into our speed run. We'll show these things first just through the code. I have some Jupyter notebook open here, or Jupyter Lab open here with input data and output data that I'll just run through very quickly, and then we'll show it in the Nextmv environment. So this is our input data to this problem. And this is particularly the input data to the estimator. And so that input data is, as described before, things like date, region, price of avocados, sales. So this is historical information, and whether it's peak demand. And it's by region, so it just have a bunch of these kinds of records, which we're fitting some machine learning model to, some regressor. And I don't necessarily want to care what the structure of that regressor is. It could be linear regression, it could be a decision tree, it could be a neural network. I just want it to work well, right? So if I look at the code for fitting this, this is an example for linear regression. And what you can see we're doing here is we're using the Nextmv integration library for scikit-learn. And what that allows me to do is instantiate a machine learning model to train from command line options or cloud options configuration that map to that scikit-learn model. So this sort of handles all the plumbing of saying what I want, these various parameters like maximum depth, for example, or maximum number of leaf nodes in a decision tree to be, and it handles all that plumbing for me. So you can see here, we're just loading the options, and we're loading that input data then that I showed you a second ago. And this is where we're doing a little bit of data preparation, feature engineering on rectangular data frames and pandas, like we normally would in a data science environment. We convert categorical data features into dummy variables. And then we fit the model. And so this is just scikit-learn. We're just using scikit-learn standard fit method. And then what we're doing is writing out the estimator as data. And this is kind of where decision ops starts to differ a little bit from ML ops, because here that estimator is a data artifact. It's a data product that needs to be saved and loaded later and swapped. So this is the linear regression version of this model. And if I look at the output for it, what it gives me is this JSON blob, with the class and so on and so forth, and these mappings that allow me to reconstitute it in a different context. And you can see here, it's just got a bunch of different coefficients for a bunch of different features. So it looks kind of like what you would expect it to look like. Now, let's say I want to sort of increase the complexity. I can see here that, the goodness of fit for this particular model is only 0.62. I'm not going to get into any of the machine learning data science-y parts of this, but that's not necessarily a very good model. So I want to increase the complexity of it. And I'm going to move over to decision trees. This is the Nextmv integration for decision trees. And we can see here, we're just loading the scikit-learn ensemble package out of Nextmv. This is its integration. And we have essentially the same thing, right? Except it's we can use gradient boosting or a decision tree or random forest or something like that. We're loading command line options or configuration from Nextmv Cloud, and that helps us sort of instantiate that into a model that is pre-parameterized and then can be trained on the input data. And so again, we're loading those options. We do some data preparation, feature engineering, whatever. We call fit, and then we save that estimator out as data, right? And so now what we look at is a different kind of estimator, which has different fields associated with it. So this is a gradient boosting regressor. It's got 50 different estimators that are trained. Some of those, some of the fields on those estimators are numeric, some are not. So this is like a code block that's actually serialized. And we can swap that in place of, say, the linear regression later. All right, so that's the fitting part of this. I'll show all those things in the cloud in a second. What does the optimization look like? So this is, again, a Gurobi model that we've adapted. And you can see here, we're also pulling in our Gurobipy integration, which does essentially the same thing as the scikit-learn integrations. It allows us to load Gurobi options from the command line or Nextmv Cloud and sort of pre-create any result statistics that might be interesting to us and that sort of thing. We're also using Gurobi ML and Gurobipy Pandas, as you can see in this block here. All right, let's scroll down to the main function here. So you can see I'm loading Gurobi options. These are just mappings to Gurobi solver options from the command line or from Nextmv Cloud. Makes it easy for me to do things like set the gap in my configuration, time limit, et cetera, turn on different heuristics. And then when we actually go into the solve function, what we're doing is deserializing that estimator and sort of reconstituting it into a scikit-learn object, right? And so this doesn't particularly care whether it's a linear regression estimator, a gradient boosted regression estimator, a neural network. Doesn't really matter. It'll just give me the correct thing, and then I can hand that off to Gurobi ML. We're also operating directly on data frames. So I'm loading in the region data here as a pandas data frame, and that allows me to use the Gurobipy Pandas open source project to add Gurobi variables as columns. And so this is very nice. Our data science world and our optimization world are starting to look very similar here. We're both operating directly on rectangular data, which could be grouped or not. And so we're essentially taking out constants and just putting in variables. And we're saying to the solver, you can set these variables. And what I want you to do is explore the relationships and trade-offs between them using a trained machine learning model. And so you can see here, we're setting the quantity of avocados sent to each region, the price to set them at, expected demand, sales, and waste, and they're all just variables. So they can be independent or dependent variables, sort of depending on the model structure. Now we're adding constraints to that model. And so these are just standard optimization constraints like you'd expect. The quantity can't exceed the total supply of avocados. Sales is dependent both on quantity and demand. And waste is essentially how much do we ship minus how many do we sell, right? So if there are unsold avocados, those become waste. And then we have an objective function, which is essentially revenue minus cost. So that's our profit. The magic happens down here where we're asking Gurobipy or Gurobi ML to add a predictor constraint. And so remember, we reconstituted that estimator. It could be one of a different number of kinds of estimators from data that we trained earlier. And we're now just saying, okay, Gurobi ML, add a predictor constraint to this model that explores the relationship between demand and price. And so that's what that's doing here. And it could be any number of the different kinds of estimators. And so we can swap in different estimators and see what happens. Then we optimize and add our decision variables to an output data frame and just convert that into JSON output. All right, this is what the output looks like. And you can see that basically a solution is for each region. How many avocados in millions do I ship there? What price do I set them at? What do I expect the demand, sales, and waste to be, and the revenue? And then I've got aggregate versions of this at the end. All right. When we start to look at this in Nextmv Cloud, you can see here that I have an app that I've created called MLOR connectors. And what I've done is set up different instances of that app for different estimators, and then a single instance for the optimizer. So each one of these estimator apps corresponds to a different regressor. And they will all take the same input that we showed earlier, but produce different outputs, which include the serialized regressors. And so here I have a linear regression estimator. There is no configuration for that because I'm just letting it do the default thing. But for my decision tree regressor, I'm giving it a max depth and a max number of nodes. For my gradient boosting regressor, I'm also giving it a number of estimators. And if I added other estimators, I would have a different configuration for those here. But the output of any one of these estimators can be the input to this optimizer, which is where Gurobi comes in. Let's look at one of the runs. So this is the linear regression estimator, and you can see that it produces a result that was kind of like what we looked at earlier. It has that serialized estimator in it. And you can see that it has the R² value and so on and so forth over here. If I switch over to decision tree regression, that has a little bit more statistical data, you can see the R² is going up to 0.92. So it is a better fitting model according to this metric. I could also add things like cross-validation here and stuff like that. And if I want to go up further in complexity, I can get a better fit out of this is a gradient boosting regressor, which has a number of estimators that are tied together. And that gets me up to like 0.96. And so each one of these has produced a data artifact, which I can now use in Gurobi. I can just swap between them. All right, let's look at some optimization runs. So this is an optimization run of the pricing model using that linear regression estimator. And what we can see here is that Gurobi machine learning add predictor constraint adds 120 or creates a model with 120 variables total, 33 constraints. It runs pretty quickly, a couple of seconds. And my objective value is 25.6. I believe that's in the millions of dollars, right? And so this is my lowest fidelity model. And this is what it is estimating they'll get in profit at the end of the day. I can look at my logs and I can see, Gurobi is solving this model and it solves it fairly quickly and gets decent bounds and so on and so forth. And so the interesting question now is, what happens if I increase the fidelity of that estimator? Do I get better solutions or not? In this case, when I move up to decision tree regression, my run duration is not hugely impacted. It's about 3 seconds. The model does get bigger. We're looking at a 2,120 variable model. And my objective value actually goes up to 38.6 million. So increasing the fidelity here, at least from the optimization perspective, is estimating that I'll get quite a bit more profit. And then finally, if I go up to an even higher fidelity model, this is gradient boosting regression. Again, the expected profit does go up again, but there's a trade-off here, which is, I set a time limit here of 10 minutes, and the solver wasn't able to prove optimality within that time. So it could have done better, potentially. And you can see here that the size of the model exploded. It went up to 162,000 variables, right? And so one of the interesting aspects here is you're not just looking for machine learning models that fit really well and generalize really well. You also need them to work well inside of the optimization. And the only way to understand how that's going to happen is to test them all together. And so this swapping between different models becomes actually fairly critical. I can also run what we call a scenario test. And so you can see here, I'm just testing the different models and I get a pivot table back. So this shows the different embeddings of linear regression, decision tree, and gradient boosting. And I could explore different options here too, like cross-validated scores and whatnot. All right. So that is the end of our speed run. What just happened? So we took pricing and demand data, and we fit 3 different machine learning models. Each one of those produced a data artifact, which could then be re-ingested later or loaded later and put into an optimization without having to think about what type of estimator it was. Those estimators explain the difference between price and demand elasticity. And then we essentially used them to give the optimizer more information about the environment in which it's operating in and start to make some of those trade-offs and calculations itself. We tested the 3 different estimators that we gave it, and we chose between them. In this case, the highest fidelity model gave us a better profit, but there was also a trade-off that it had a longer runtime, and so there are compute questions there. This was made possible partly because we have the ability now to both save and load these estimators and swap between them seamlessly and then test them in infrastructure. And then ultimately what this allows us to do is optimize transportation, distribution, and pricing of avocados. So, this is all the tool. There are a number of tools that are working together here, right? There's scikit-learn, there's Gurobi, there's their Gurobi machine learning library, Pandas. And we're seeing like the Nextmv part of this being is essentially sort of the plumbing, the infrastructure. How do we train a bunch of different models? How do we save them and seamlessly swap between them and choose between these different estimator embeddings? So over on the scikit-learn side, what we're currently supporting is any of these regressors. So linear regression, tree-based, and neural networks. You can load these things into different environments. You'll get different ways of interacting with that machine learning. So for example, what we showed today was using Gurobi machine learning and the Gurobi context. What that means is that these estimator models become linearized. So they are sort of translated into linear inequality systems and given to the optimizer in a new form, right? So like that scikit-learn estimator, when you give it to Gurobi machine learning, functionally it is essentially gone now. And Gurobi has all of that information embedded, right? It's been translated into the language of mixed integer programming. And Gurobi sort of has gained that knowledge. You could think of it like downloading the helicopter manual in the Matrix, right? And Skip also has a library that does that called PySkip-opt-ML. So in this context, you could the reconstitution or the deserializing of that scikit-learn model is going to work essentially the same way. It's just now using the Skips library for embedding it in the model. And they work in similar ways. You, of course, have very different power between like commercial and open source. There are other approaches too, where, for example, in the like Seeker or Hexley context, what you can do is you can query the estimator directly. And so there's pros and cons to these things. We gave a tech talk with Seeker not too long ago where we showed essentially sampling from a probabilistic forecast. Now, in that case, the solver may not have direct knowledge of the structure of the machine learning model. And so it's essentially querying or asking the machine learning model, what do you think of this option? If I set this price to here, what do you think the demand will be? And so there's different different sort of costs and benefits to doing things these different ways. From an infrastructure perspective, what we're trying to provide is essentially something where you can build all these different apps and plug different estimators into different models in a seamless environment and swap between them as needed and sort of do that exploration in a managed and sane way. And so that's what this is showing is sort of you have all these different apps which use different technologies. They could be machine learning or optimization technologies, and you can plug them together sort of as like cookie cutter components and not have to think too hard about what it means to swap between one app and another. So takeaways. Embedding ML models into OR gives the optimization solver more information about the world. What we are essentially doing is saying, here is data, machine learning, go help me understand this data and infer something from that understanding, from that examination of that data. And now, optimizer, take that information and encode it some way that you can use it. So that's impossible with this embedding, but it's not really a panacea, right? It's extremely powerful, but you also really have to understand how these components interact. Different fidelity models might give you very different results. You have to understand what that means both in terms of computation time and the ability of the solver to interact with those models, as well as like, are these models producing things that are reasonable at the end of the day, right? We saw that going up in fidelity increased the profit in our optimal solutions, but is that real? So we have to understand if that's a real thing or not. And ultimately what we want is sort of a seamless way to parameterize these models, switch among them and test them, and figure out what's best for your problem, for your optimization, and for your business. And so that's what we're trying to provide here. All right. And that is the end of my talk. So now I believe we have time for Q&A.
Yes, just a few minutes here. So thank you, Ryan, for covering all of that. That was quite a bit for half an hour there. So there are two questions that I want to make sure to surface that I think you've touched on, but for the sake of making sure that we cover them. Does it matter which optimizer you're using when you're translating the ML model into kind of a readable format?
For the machine learning part of it, not really. You can, anything that's sort of savable, right, can be re-ingested later. What matters is, what you're going to do with it after you've re-ingested it and loaded it. And so if you're doing something like the Gurobi machine learning approach, linearizing, what you have to understand is that there is a translation process of moving that machine learning model into solver speak, right? And that's very powerful, but it does require understanding of what's going on because there's going to be trade-offs, and it's awesome, but with great power comes great responsibility, right? If I'm linearizing an enormous gradient boosted, regressor, I might end up with millions of variables, right? And so am I able to solve that? If not, do I need to change my model in some way? There's also interesting caveats that come with machine learning, embedding machine learning models that aren't directly tied to the objective function, and sort of errors in that linearization process. So I like to think of this as this guarantees that we're all going to have jobs going forward, because as our domain sort of expands both from the data science into the optimization world and the optimization world into the machine learning world and so on and so forth, right? Um, it gets more complex, but also more fun.
Excellent. I know we're running up against time, but I am going to try and slip in a couple more questions here. There's one
Go
that
for it.
just came in the Q&A that says, Gurobi ML already facilitates connecting scikit-learn and Gurobi. Can you explain the advantages by using Nextmove as an additional layer?
Yep. Essentially, what it is giving you is a way to uh, do the decision ops part of this, right? And so, if you look at the examples on in the notebooks online, what they're essentially doing is training a single model, right, and then fitting that machine learning model into the optimization. The reality is, if I'm doing this in the real world, I have a number of concerns between the loading of the data and the formulation of the model. Those concerns are things like, does the machine learning model that I'm using generalize well? What are different cross-validated scores on it, so on and so forth. Once I have a model that generalizes well, is it small enough to embed it in an optimization in a meaningful way? Once I embed it in an optimization, how long is it going to take to solve that optimization? You could have very good or well-fitting machine learning models that once they're in the optimizer, they perform poorly, and sort of either need, the model needs help, or using a simpler model may actually get you better results. So what we've found is that testing and embedding loop, it requires a lot of the same thinking like ML ops requires for machine learning. And so this having infrastructure and tooling around that is very useful for facilitating that and making it fast and easy.
All right, and there's another one here, and I'm going to make hopefully I convey this one correctly. So, Ryan, the model that you showed only used linear regression. Could it also be used with more variables, fixed and random, and for multivariate variables?
Actually, the optimization model, we showed a few different outputs. One was this was probably lost. So let me just reiterate it so it's not lost. There were three different runs that we showed of the optimizer. One embedded linear regression, one embedded a decision tree, and one embedded gradient boosting regression. The linear regression one was the simplest of the three and ended up with a fairly small model. And as we went up in fidelity, the models got bigger. So by the time we got to gradient boosting regression, it was not able to prove optimality within 10 minutes, though it was able to find a better feasible solution. And I'm not entirely certain that I understand the multivariate question. So maybe we could take that one offline.
Sure. And I'll ask one final one that from earlier, but you mentioned decision ops earlier, Ryan. Can you speak to how people should be thinking about how what you showed today potentially interfaces with ML ops workflows?
Yeah, we've been thinking a lot about like what is, we've come to the decision ops term and world from the optimization side, right? So how do we orchestrate solvers? How do we test solvers and optimization models for production use? As we've sort of started to move a little bit more into the integration between ML and OR side, one of the things that's become clearer to us is that as you start to move into sort of adjacent territory with ML ops, one of the big differences between these worlds is that in ML ops, sort of the fundamental input and output is data, right? You're taking data in from somewhere, usually from observations or databases or whatever, and you're typically producing point estimates, maybe multiple point estimates, maybe even a probabilistic forecast, but typically point estimates, which are also data. So it's sort of a data to data, translation. Once we start using machine learning in the decision ops context, the fundamental unit for ML is actually now the model, right? So it turns it on its head a little bit and focuses it in a different place, right? And what we want to be able to do is treat these models as essentially data artifacts that can be used by optimization for decision making.
All right, excellent. I know we've extended our time just a little bit, so we appreciate everybody staying with us so far today. Ryan, thank you very much for walking through the presentation. For everybody that's tuned in, this session was recorded. We will be sharing it out afterwards. If you'd like to join our next Tech Talk on November 21st, we'll be doing a roadmap review and preview at Nextmove. So that should be an excellent roundup for all the goodness that has shipped and all the goodness that is coming. So again, thank you everybody for joining today. Ryan, thank you very much. Until next time.
Thank you.